We're waiting for the director just to show up. Please, Juan Carlos. Yeah, we can start.
You just tell me when to go and I'll start.
So welcome everyone to this special seminar that we call here the Coloquio de Impacto Mundial. And also it joins to the celebration of the International Year of Quantum Science and Technology, as you know, this year. And today we have the pleasure to have Professor Hugo Ribeiro from the University of Massachusetts at Lowell. Let me just say a few words about Hugo. Hugo did undergrad and master studies at the EPFL in Switzerland. Then he moved to Aachen at Constance for a PhD under the guidance of Professor Guido Buchard, working on control of spin qubits in electrically defined quantum dots. Then he went for a postdoctoral position to Basel University of Basel in Switzerland, working on the coherence of whole-based qubits in self-assembled quantum dots. Then he moved to McGill University in Canada to work in quantum transducing and quantum state transfer and quantum measurements. And finally, he did a postdoctoral. He held a postdoctoral position at the Max Planck Institute for the Science of Life in Erlangen, in Germany, working in reservoir engineering for many-body quantum systems and also in quantum control of engineering quantum systems. Finally, he is now assistant professor on 2022, right? Yep, the University of Massachusetts at Lowell, and he's an expert on quantum control of multi-qubit many-body system, topological operations with non-Hermitian system, non-Markovian dynamics and open quantum system, and quantum sensing. So, welcome, Hugo. Very, very pleasure to have you here. The floor is yours.
Thank you so much, Carlos, for the kind introduction. Thank you, everyone, for being here. So before I start, I just want to tell you how the invitation happened from Carlos' side. So Carlos said, "Oh, Hugo, you're coming to Mexico City to the conference that we're organizing in the main campus of UNAM. So it would be nice on Friday you come, you can talk to my students." I said, "Yeah, of course, like I'm there. Let's go talk to the students." But then on Wednesday we're having dinner. Don't laugh, it's not funny. And I find out that actually I'm leading a special seminar that is called Colloquios de Impactos Mundiales. So no pressure there, right? But I was like, okay, it's just a seminar, so everything is fine. Then I come here and then people tell me, oh, you're going to be recorded, which I was, again, not expecting. So, pressure has been building up and building up. So I hope I can do justice and actually introduce you some of the work that we're doing related to quantum technologies and quantum control, right? Okay, so my first slide, before I go on, I just want to advertise the picture that you see here. You're probably wondering what this is. So this is the shell of the nuclear reactor of UMass Lowell. And very recently, the city and the university, they partnered with street artists, and they can come and just paint our buildings. So then instead of having these very gray, dull buildings, we actually have something that starts to look modern and nice. So I just wanted to show you this. All right. So let's jump right in and ask ourselves, what is a computer? If you have to describe to someone, to a lay person, what a computer is, what would you say? A machine that computes, exactly. It's a machine that you feed in some information, there is some black box, and outside you have your information that has been processed. All right? So the typical example, times 7, you feed that into your machine, and it tells you 42, and you're very happy, and you move on, right? Now, if I want to use such a machine as a human, right, the information that I'm communicating to the machine is 6 times 7. The machine will not understand that. The machine needs a language that can translate between human language and machine language. And this is done in binary. So basically, computers, they have their own language where you use binary encoding of information, such that now when I tell 6 times 7, like in the input here, there is a translation that is made such that 7 now becomes, 00111. You all know how binary works, right? It's like the decimal system. You're comfortable with that, right? And you have 6 here also, and you can multiply those and you're happy. Now, this is very nice, and that's probably how a computer scientist would explain to a layperson how a computer works. But as a physicist, what we ask ourselves is, okay, what are 0 and 1? What are the physical degrees of freedom that I use in such a physical system to encode information? So in a classical machine, it's literally a switch. Okay, you have a piece of electronics that is called a transistor, that is such that if you apply a threshold voltage, there is current that flows to this transistor. And then you can say, okay, if current flows, I'm going to say that this physical state corresponds to my 1 in binary language. If the voltage is below the threshold, no current flows. You can detect that, and you say, okay, that's the state that corresponds to my 0. And with that, we can do all the computations that you're used to do, your simulations, browsing the internet, writing text. But there is a question that was raised by Feynman that asked, if nature is quantum, then if I use such physical degrees of freedom that are purely classical, I cannot simulate nature. I would need to try to encode information in a quantum degree of freedom, and only then could I efficiently simulate quantum nature. So how do we go now from bits to something which is quantum? Well, we'll just do it like CS people will do for the introduction, and we will introduce a qubit. So the way that you need to think about the qubit is a 2-level system that you can depict here on a sphere as a vector of length 1 that can point at any point on that sphere. And you choose 2 special directions, say the south pole to encode for your 0 and the north pole to encode for your 1. But because this is quantum, it can be in any possible superposition, such that you can have a superposition here of 0 and 1, which again, you can represent this as a vector in some direction with an angle theta and phi on the unit sphere. So how do I do binary logic with that? Because now I have a problem, right? Like here I have 0 and 1, but we just saw that the way we humans translate information to computers by saying it's 0 or 1, not both at the same time. So the way we get around this, it's with a measurement. You have a quantum system, right? Just like you did for the classical bit, where you were looking at current and asking, is there a current or not? Here you simply ask, well, where is my arrow? Is it more on the north side or is it more on the south side? So when you measure that, the probability of having the system being more on the 1 side or on the 0 side will depend, of course, on the amplitude of the quantum superposition. And once you measure that, then your qubit will be in the 0 or the 1 state. So after measurement, you go back to what you like. You have a state that is 0 or 1. But this is not why quantum computers are faster. It's not because I can use quantum superposition. The reason quantum computers are fast is because I can use entanglement. So let's try to introduce briefly what entanglement is. Imagine now that I have 2 qubits, and they have those 2 states represented by those 2 arrows. And those 2 states, they have a certain probability of being measured in the 0 or the 1 state. But you agree that if I know those 2 probability distributions of measuring 0 and 1 for each of the qubits, I can build a joint probability distribution for all possible binary strings. So I have the probability of having 0, 0, 0, 1, 1, 0, and 1, 1, which in this case you can simply build by multiplying those probability distributions. But unfortunately, there are states for which I cannot do that. There are states that are very special, and the probability distribution of measuring those bit strings, I cannot describe that as the probability of having qubit 1 in a certain quantum state and qubit 2 in another quantum state. So that's entanglement. That's when I cannot describe the probability distribution of measuring these bit strings as the sum of individual constituents. And now we can make a simple, well, Gedanken experiment, as we say in German. And let's say that I give you the entangled state that was on the previous slide, and I ask the following. I have my device that can measure, and I will start by measuring the state of qubit 1. And let's say if I measure the state of qubit 1 to be 0, can you tell me what happens to qubit? Exactly, it will be 1. So it's very curious, right? Because the bit string 0, 1 had a probability of 1/2 of being measured, but you realize that as soon as you measure one of the qubits, you have probability 1 of knowing what the other state is. Okay? And obviously, if you measure 1, then you know that the other qubit was in state 0. So why is this important? Well, it's important because that's what quantum computers, they're all about. Quantum computers, what they want to do is to take n such qubits. They want to create a massive entangled state. But this massive entangled state is created in such a way that the probability distributions for all possible bit strings that you could possibly write are such that one of them is much larger than all the others. Such that when you measure one of the qubits, the state collapse to that bit string. And if you did it correctly, this bit string is the answer to some information that you would like to know about. Okay? So that's the basic principle of how a quantum computer works. So now the question becomes, all right, how do we create this entanglement? So there is many different models of quantum computing. Here, I'm just going to introduce what is called the circuit model of quantum computation. And the idea is that I can generate entanglement by only doing 2 types of operations to my qubit. The first type of operations is what we call a single qubit gate. So this is you taking your arrow on the sphere that I show you and just rotate it anywhere else on that sphere. The other type of gate that you're allowed to do, or that's the only other gate that you need in this model, is what we call the control gate. So this is a gate that will induce a rotation on a controlled qubit. So in this example that you have here, this would be that 0 to state will undergo an operation that is defined by the state of the first qubit. So for this special gate, what it does is if qubit 1 is in the 0 state, you do nothing to the second qubit. So 0, 1 goes to 0, 1. But if the state of that qubit is 1, then you just do a flip of the second qubit. So now I will just guide you what happens if I run this circuit in time. So let's say that I do this first rotation here that just prepares an equal superposition of 0 and 1. So that means you start in the 0 state and you rotate to the equatorial plane. So you have a 1/2 probability of being 0, 1/2 probability of being 1. And now you apply this conditional gate. You end up what we call a Bell state. This is a maximally entangled state. Okay, so you see that now from having qubits that can be described completely as individual constituents, after these first 2 gates, you already have something in the first 2 qubits that you cannot do that anymore. They're entangled. And as I go on doing more and more of those control NOT gates, I generate larger and larger entanglement. Okay, so here I have what is called the GHZ state, which again is a maximally entangled state. So that's the basic idea. So why do we really care about that, right? I mean, after all, I am doing some quantum, and I use a classical computer right there to make my simulations, right? So let's look at a simple problem that is actually very hard to do on this machine right here. Say I give you 21. 21 is what is called a semi-prime number, meaning that there is 2 prime numbers that I can multiply together that give me 21. Can you tell me what the primes are? 3 and 7. That's pretty easy, right? Okay. Can you tell me now what the prime number is? No, you cannot, right? But probably you thought, oh, it's okay, I'll just ask my classical computer to do that for me. Well, it's going to be very, very hard as the number of digits of these numbers gets growing and growing and growing. So here is actually the two primes, if you're curious about it, right? That's the two numbers. And obviously, what I did was not trying to get this number and then those two numbers. I did the reverse operation, because if I pick two primes, I can easily multiply them on that machine right here. So basically, the time it would take you to factorize numbers like this grows exponentially. So the more digits you have, the more time you need. All right? And well, is this just some kind of, quantum computer science theorem, some mathematical abstract thing that I should not care about? Well, not really. You actually use this on a daily basis. If you're texting, if you're connecting to your bank, you're using the fact that it's very, very hard to do semi-prime factorization. So here is an example how this works. You want to send a message to someone, then in your phone, behind the scenes, there's a public key that is going to be generated. This public key is just a very long semi-prime number. Now, the person that you're sending the message to, he knows about something more. He knows a private key, right? So the private key, basically, it's the two primes that when you multiply, gives you the public key that is used for encryption. So there is a mathematical operation that uses the fact that this n exists on your phone to scramble the message is sent. And now, because you know the private key, you can easily decode it because you know one of the two primes. But if you don't know this P and Q, and you spoof a message, right, and you try now to read the message by decoding it, it can take as long as the age of the universe to find something. So here is an example. In 2020, one needed 200 and 700 cores to decrypt a number that had 250. If you ask your bank, what encoding are you doing? You're doing 2048. Okay? So you see that on those time scales, what this means is if you send a message to someone like, I don't know, please buy NASDAQ now, because I have some private information that tomorrow, the market is going to skyrocket, and you don't want other people to know, it's okay, because even if I spoof that on the best classical machines that I have, it will take me a very long time to be able to decrypt that message. But on the other hand, if you would have a quantum computer, you could decode that message in seconds to hours. And this is because we know that there is special types of problems that we can run very efficiently on those machines. And this is why Army, for instance, in all the countries, they're very interested in developing such machines to basically do cryptography and break other people like encrypted messages and encrypted information. Obviously, there is other applications. There is other types of problems that we can do, but don't imagine that the quantum computer, right, you're going to be playing video games on it. That's not going to happen. That is there is very few purposes exactly, right? Like, what am I doing? There is very few purposes that the machine can do that we know as of now. We're still right now discovering more and more applications to those. But what quantum computers are very good at is optimization problems. So here you have a map of Germany, and the problem here is the travel salesman problem. You have someone that needs to visit a lot of cities, and you're wondering what is the shortest path between those cities. Quantum computer is very efficient at solving that. Also, like in biology, like for simulations, drug discovery, simulate physical systems, right? If you go to someone that is a condensed matter physicist and you ask, what is the ground state of a high-TC superconductor, people cannot tell you. But if you have a quantum computer, you can actually simulate and guess what the state, or measure directly the state, what I should say here. Then there is, of course, secure communication, which is, again, like what I showed you before, right? I told you that you can spoof the keys. And then if you have a very powerful machine, you can decrypt them. So there is ways that we can actually generate those keys quantum mechanically in such a way that you would immediately know if someone took the key told your message. And finally, a kind of a spin-off that is very new is sensing and metrology, which uses like concepts of quantum computation, sense magnetic and electric fields with a sensitivity that is much, much higher than what we can do with classical systems. Okay, so all of that is very nice. We know how a quantum computer works. We know what type of algorithms a quantum computer can run. So why don't we have a quantum computer yet? So here is a few reasons why. So you remember that at the beginning I told you, you can think of a qubit as a two-level system and you can represent it as an arrow of a unit on a unit sphere, right? Well, the reality in the lab is very different. Qubits, they're not truly two-level systems. They're close to actually artificial atoms. Because they're artificial atoms, they're not true two-level systems. They actually have a bunch of discrete levels, each associated with an energy that is quantized. So how do I use that to define a qubit? Well, I say I'll take my ground state, I'll take my excited state, that's going to be my atom. Now, an atom has a dipole element, right? So meaning that if you shine electromagnetic radiation, you can excite the ground state to the excited state. That's how you're going to do those rotations. But when you do that, then usually you're going to come with an electromagnetic wave that oscillates at the frequency omega d and has some envelope that is going to dictate by how much you rotate. So you want omega d to be equal to the transition frequency, right? The issue is that if you look now at the difference in frequency between the 2 and the 1 state, it's not 1, 0. That's a good thing because this kind of guarantees me that I'm not exciting the second level, but it's also not far off from the omega 1, 0 transition, meaning that you have a finite probability of exciting this second level. And you see that this would be bad because in that case, how can I define a qubit? A qubit is a two-level system. If I start putting population into excited states, I'm not anymore doing quantum computation. Is there a solution to that? Well, yes. What I need to do is basically I need to do those gates very, very, very slowly. If I do it very, very, very slowly, the amplitude of transitions to the excited levels, like here the 2, for instance, is going to be exponentially suppressed. So everything is good. Almost. So what I show here is, of course, like a kind of a cartoon to explain the physics, but this physics really happens in a lot of platforms and platforms that are strong contenders to implement quantum computers. So here you have the example of spin qubits in silicon, where you want to use the spin of the electron as the degree of freedom to encode 0 and 1. So spin up 1, spin down 0. But in these systems, again, you want to stay in the subspace of 1001, meaning that you have one electron in this example on the left quantum dot, no electrons on the right quantum dot, and vice versa. You have one electron on the right, 0 on the left. You start shining electromagnetic radiation, and suddenly you create a state that has both electrons on the same quantum dot. That is a singlet state. So this, again, you're out of the computational subspace. You're done. Your quantum computer is dead because you don't know what to do. Here is a very famous qubit, the transmon qubit. This has been very successful in demonstrating a lot of achievements in the field by Google and other companies. And the transmon, you can really think about it as an anharmonic oscillator, right? So it's kind of a harmonic oscillator, then all the frequencies, they would be the same. But because it's slightly anharmonic, the transition from 1 to 2 is slightly detuned from the transition to 0 and 1. But okay, if I can do my gates slow, then what's the problem, right? Because you just told us that what makes a quantum computer fast is the fact that the algorithms, they are different. That has nothing to do with how fast you do your gates. So here comes the caveat. I showed you physical systems. Physical systems, they are not isolated from an environment. Just like your cup of coffee in the morning, when you put it on your desk, You come 1 hour later, the coffee is cold because what you've been doing is putting energy into the environment. So qubits, they can do the same. So you could have, for instance, a qubit that is in state 1, and you let it be for a while, but when you come back, well, the qubit is in the 0 state. And this happens like randomly, but if you run an experiment where you prepare the qubit in 1 and you measure what is the probability of being in 1, and you do this many times and you average over all of the outcomes, what you find is the standard relaxation result, where you see that the population of the excited states decays exponentially with time. The environment can do a second thing. If I prepare a superposition of 0 and 1, then quantum mechanically, this means that there is a well-defined phase between the 0 state and the 1 state. But if my level, they jitter a bit, then I'm going to lose this phase. And if I lose this phase, then my qubit that was supposed to be allowed quantum superpositions just becomes a coin that you flip with a 1/2 probability of having heads, 1/2 probability of having tails. So in both these examples, you just lost information that you stored on the quantum computer. So you see that this idea of doing the gates as slow as I could does not hold anymore, because I have limitations from the environment, and I am limited from below by the gate time that I have at my disposal. And that's where I come in, because what I try to do in the group is basically, how can I control those qubits in gate times that are much faster than the typical decoherence time? So this relaxation time that I showed you before, the dephasing time that turns a qubit into a classical system, without without having my system leaking to those higher excited states that are available. Okay? So the problem that I studied is very simple. I just have a time-dependent Hamiltonian that I can split into two parts, the H0 and a V. And the H0, what it does, it kind of describes the ideal dynamic that you want to have, right? Like when you apply a gate, everything stays nicely in the 0-1 subspace. So this I kind of depicted here in this very large Hilbert space in black that contains the state 0, 1, 2, 3, etc. And what you want is just to say inside of this orange box that is all the possible states that you can write as superposition of 0 and 1. So H0, what it does, it picks a state inside of this orange box and it maps it to another state in the orange box. And I'm happy I'm doing quantum computation. Unfortunately, I have this term, the VBAD. And what the VBAD does, well, it maps a state inside of the continuous state, so superposition of 0 and 1, and maps it now into something which is a superposition of 0, 1, and 2. And this is really like very generic. It happens in a lot of systems, and it really comes in different flavors, like couplings to non-computational states, non-adiabatic errors, crosstalk. All of those are problems that the community is trying to solve right now to make sure that qubits, they behave the way we want them to behave. Okay, so now I could explain to you what are the generic techniques that I use in the group from a very quantum mechanical perspective. I'm not going to do that. We're going to do it classically. And classically, you're going to have a very good idea of physically what we're trying to achieve in the group. And then I'll give you a bit more detail. So here's a problem that really translates to those qubits. I call it the waitering problem. Imagine that over summer, you decided to work in a very hyped coffee. Your boss is a very hateful person because he wants you to deliver drinks fast to the customers, but in stylish way. So what you're allowed to do is to hold a tray on one hand, and the other hand has to be on your back. You're not allowed to hold drinks or bottles or anything. So if you want to deliver drinks promptly, what do you think you're going to do? Well, yeah, you're going to run, most likely. You're going to walk with a very fast pace, right? So now if you do that and you stop at the table, what is happening to the drinks that you're holding? Yeah, they will spill, right? We can check on the video. This is really going to happen, right? You run, you try to stop, and there goes the drink. So if now you're constrained by the fact that one hand has to be behind your back and you have to hold the tray like this, right? What can you do to avoid the bottle to fly away? Lower? No, because you have to do it fast. Yes, you're absolutely right. I will just tilt the tray as I go along. Because the bottle flies away, because when I stop, the bottle has no force that can stop its motion. So Newton's laws of mechanics tells me that the bottle will just continue its trajectory. But if I tilt my tray, what I'm doing is I'm imposing now a normal force, right, that has a component that is opposite to my own motion, and the bottle will hopefully stay on the tray, right? So with a few practice runs, you can really do it. And there is your bottle. So that's what I do. That's really like the strategies that we come up in the group. We do it like physics informed. How can I use these bad interactions that I have in my system to my own advantage, such that the qubit ends up where I want the qubit to end up? Okay. So if you understood those two slides, you understand what's gonna come next in a more quantum mechanical fashion. So this is how you can parameterize the system. What I want to do is to change how the system behaves in time. And the way to parameterize that is to add to my Hamiltonian a term that we call the control Hamiltonian W. But what W does is nothing more than me tilting my tray, right? So it allows my system to explore the whole Hilbert space, meaning that if I'm doing a gate, a rotation, it's okay that at some point in time, there is some population in those excited states. As long as when I'm done implementing the gate at the final time, everything comes back where I want it to be. Okay? And okay, so this is how it works. So what we want is the W to average out, not to fully cancel. Because again, if you go back to the classical problem, fully cancel means that you're holding the bottle. But this is not allowed, out of the constraint of the physical problem that you have at hand. Okay? So what you're saying is, I don't want to cancel at all times the bad interaction. On average, I want to cancel it. That's exactly what you're doing when you're tilting, because on average, you're slowing down the bottle and force it to stay on your. All right. Now, you see that here, I kind of depicted a map that follows this purple curve, right? But that's a choice. You have thousands of such curves. And this is actually, for us, it's an advantage, because then it allows me to pick and choose a solution to the control problem that is tailored to a specific. So imagine that you have a magnetic field that you can only control the X and the Z components in time. And in this example, let's suppose that you cannot have Y, although this, it's not correct, but just like, again, a thought experiment. Well, if you can only do that, you can choose one of those blue trajectories that is actually compatible with what you can. That is the idea of the fact you can have many of those passes mapping a state to another state. All right, so how do we find that? How do we find that quantum mechanically? So yeah, this is a bit technical, so you just stop me if you don't understand, but what I'm going to show you, again, like quantum mechanically, how I find the tilting of my tray. So here the trick is to go to what we call the interaction picture. Interaction picture simply means, you remember I gave you a H naught plus a V, and I say the V is the bad thing. So I want to go to a frame, a reference frame, where the dynamics of H naught doesn't play a role anymore, because I know that this is going to give me what I want, and I just want to be left with the bad term, which in this interaction picture takes this form, where again the operator U that you have here, U0, drives the good dynamics. And now if you open your favorite quantum mechanics books, it tells you, well, if this operator commutes at all times with it, then it's pretty easy to solve the Schrodinger equation, and this would be the answer, just the exponential of the integral of that operator. If you look at that expression, could you guess what I want to impose on W? Remember, I want to cancel things on average, right? So I'm just going to ask that the integral of W in the interaction picture is the opposite of the V. Okay? So now I have a problem because I told you, let's suppose that V commutes with itself at all times. So you could ask me now, can you give us an example of that? And my answer would be no, I can't. I probably cannot cook up any quantum system that has this property. That will be take me a long time to figure that out. So it's a kind of an alien out of the problems that we have there. So what we do is we kind of use perturbation theory to find the W. And in perturbation theory, we write W as a series. And as I go along in my perturbation theory, I ask that each term on this perturbation cancels a bad term that shows up in perturbation. Again, if I make a small diagram, you start with the bad dynamics because there is the V that is there. You find the first term of the term that supposedly averages out the bad effects. You get closer, but not exact because, again, it's perturbation theory. So now you consider the new Hamiltonian that you find out that gives you here the blue dot, and you try to find now the W2 that cancels the bad effects of the new Hamiltonian, and you iterate that further and further until you come as close as you want to the state that you want to reach again. Okay. So this is nice, but it's very unwieldy because those are operator equations, right? I have the integral of operator equals minus the integral of another operator. But there is a way that we can kind of decompose that into a simple problem. And the basic idea is to say, if the matrix elements of W, I write them as a Fourier series, then what I need to find is the coefficients of the terms of my Fourier series that cancels out those integrals. Meaning that at the end of the day, this very complicated problem becomes a simple linear system of equations to solve, where in this parametrization, the M knows about your good dynamics, the H naught. The X is the coefficients that you're looking for, and the Y knows about the B, knows about the bad dynamics. So here is kind of an example. And again, I'm just going to run that very slowly to show how the technique works, to give you just an idea. And I chose one of the simplest possible problems there is in driven quantum systems. It's a true level system that you're driving with such a pulse, okay, that you can simply write as some cosine omega dt. So you know it's the cosine quadrature that multiplies an envelope. So let's see how we can apply those techniques to solve that problem and to see why this is already a problem that no one can solve exactly. So the first thing that you do is to rewrite this Hamiltonian in a frame that rotates at the frequency of the drive. So again, a classical picture is if you have a football and you are on a merry-go-round, it's on the floor and you kick. If you want to describe the physics from the perspective of someone that is outside of the merry-go-round, it becomes kind of complicated because you have to take into account that the merry-go-round is accelerating, right? Compared to the inertial frame that you're in. But if you go inside of the merry-go-round, the physics is pretty simple because from your perspective as an observer, the ball is going straight. Okay? And then what you do is you write a Fitcher's force on your equations of motion to describe the correct trajectory of the ball from the perspective of someone that is in a Galilean frame. So that's what we're kind of doing here, right? We're moving inside of the merry-go-round, and the price that I pay is those terms now that oscillate at twice the frequency. That's my Fitcher's force. So in this Hamiltonian, this term here that contains only the envelope of the drive, that's going to be my H. The terms that I have here, that's going to be my V bad. That's the Fitcher's force that prevents my ball on the merry-go-round to go straight. The delta, I don't care because the delta, I can set it, I mean, since it's in the control, what I can do in the lab, I'm simply going to set it equal to transition. So let's try with this Hamiltonian that is here, when I set delta to 0, to make a rotation of this arrow around the x-axis by an angle of pi half. And I want to do it again very, very fast. So this is what I'm going to see. So I don't really end up on the y-axis. The reason for that, it's again because of those terms here that rotate at 2 omega d. So I would like to average that using the technique that we have. So we set the machinery on. There is a very well-defined recipe on how you can do this. And the first thing that you're going to do is you're going to parameterize this operator W that allows you to average the bad effects as an operator that is compatible with what you have in the lab frame. So you see, in the lab frame, you're allowed to have a classical EM field that couples to sigma x, and that's exactly what this is, except that now you have a 2 quadrature drive with cosine and sine, and you have 2 envelope functions. Other thing that you're allowed to do in the drive is, well, you can choose whatever you want for omega d. The reason we chose the drive frequency to be equal to the transition frequency is because that's what textbooks they tell us to do, but that's definitely not the optimal thing to do when you look at the whole Hamiltonian. So if you do that, you put the machinery on, and that's what you find. You go from this kind of magenta curve where you have the envelope fx to the 2 envelopes that are here. So the prediction is very simple. You have to diminish a tiny bit the amplitude of the original pulse, and you have to add a y quadrature. And on top of, and if you do that, and now you look at the dynamics of your qubit, what's going to happen? Whatever you want. So where does this physics come from? Well, the physics comes from because when you shine radiation, the 0-1 qubit feels an AC star shift. So the AC star shift, what it does, it kind of renormalizes the energy splitting between the levels. So that's called the Bloch-Sigurd shift in the language of a 2 level. And because of this Bloch-Sigurd shift, that's the reason why you do not want to drive at omega d equals omega q. You want actually to drive on resonance with the splitting plus the Bloch-Sigurd shift. Okay? Now, why do I need to add a y quadrature? Well, if I look at my Hamiltonian here, you see that I have this sigma x and this sigma y in the back terms, right? So what this is doing, it wants the qubit to rotate out of the, say, the plane that is in the defined by the z and the y coordinate. And the idea again is let it go out of the plane, but make sure that during the evolution, you're trying to bring it back where you want it to. So basically, this y quadrature here, that's me tilting my hand. Okay. So is this really a much better way of, implementing the gate? I mean, visually, you clearly saw that I was not on y. If I just do the naive thing, if I do this kind of control techniques, I end up where I want. We can actually quantify that in a much better way by using a quantity that is called fidelity error. And if you're not familiar to that, what it does is imagine that you have the arrow somewhere and you apply a rotation. And this rotation supposedly would lead you to some desired state. But in reality, what it does, it brings you to some other state represented here in blue. Now, on the sphere, you can define a distance between the tip of this arrow and the tip of that arrow, right? So that's exactly what this fidelity error kind of measures. It's the distance between the state you would like to have and the state that you can actually implement in the lab. And if I plot now this quantity as a function of gate time, then you see that the fidelity error, so between what you would like to have, what you actually generate, is much, much smaller once I implement a pulse that takes into account the function. And as expected, as my gate time becomes shorter and shorter, then my fidelity is way, way below what, the naive allow me to do. Obviously here, the fidelity of the pulse that is corrected still grows with gate time because I'm doing this up in perturbation theory, right? I'm not finding the exact W, I'm finding W up to a certain order. So as I go faster and faster, there's more and more terms that I should be correcting, but because it also gets, tedious to do it, I just truncate at some point that gives me an error fidelity that is low enough for quantum application. So this obviously was a very academic problem that I just showed you to give a flavor how this kind of strategy works. But now what this strategy allows us to do is to face real problems that are happening right now in the labs. And one of those is what we call the crosstalk problem. So the crosstalk problem is as following. Imagine now that you have a real quantum architecture with qubits that are placed in a lattice. You would like to access only the central qubit, right? You would like to generate only a rotation of this qubit. But you're shining radiation. Radiation is an electromagnetic field. So in space, it's not localized, it has an extension. So the qubits around, they will feel this radiation and they will start to rotate a bit. So you see that you're not doing what you want to your computer. So we are hoping to use those techniques to tackle this type of crosstalk problems. And obviously, this is not only the case when you're trying to do these single qubit gates, it also happens when you're trying to do these qubit gates that I showed you at the beginning. So now what you're trying to do is to entangle those two qubits. And again, you can use EM radiation to manipulate the target depending on the state of the. But if in your platform you cannot turn off the coupling between the qubit here that you would like to entangle with this one to a neighboring qubit, then you're not just entangling those two, you're actually entangling those three. So you're generating more entanglement that you want. And again, this is bad because this will break the way the algorithms they run. And this is also something that with those techniques, we hope to be able to, give an answer and tell people, okay, this is how you need to control to make sure that you're entangling those two up to a certain degree of fidelity or. Okay, so with that, I come to my conclusions. So I hope that I could convey you a bit what quantum technologies are all about, and that I showed you that we're still very far off of actually having a real quantum computer, because controlling those quantum systems is actually very, very hard. And here I just spoke about errors that come from the control itself. But remember that I told you that qubits, they feel the environment. So those things, they go hand in hand. I cannot really separate them. So the type of problems that we are facing in terms of are really, really complicated. And to be honest, in my humble opinion, I do not think that a quantum computer is something that is going to happen in spite of what companies want you to. Okay, and with that, I thank you for your attention.
Thank you very much, Hugo. Very illuminating talk. We have room for questions.
In your examples, you know what the bad Hamiltonian was.
I do.
In actual practice, do you know?
I mean, that's a very good question. And no. So we have models that, can reproduce most of the experiments that are done. But it's true that some systems to know the Hamiltonian, specifically the parameters of the Hamiltonian, right? This is not necessarily known. But the good thing about it is that these techniques, they have a certain kind of robustness towards parameter imprecision. So if you know, on average what the coupling is between two states, and it has a statistical uncertainty, the protocols can still give you an advantage. It doesn't die completely off. Yeah, you're welcome.
Any other question?
Thanks by your talk. My question is the following. If I understand correctly, you are doing something, let's say a Hamiltonian, maybe in the environment, trying to control this quantum bit. But the question is if you cannot use another quantum bit, because when you work in this spacing or all this stuff, there are many ways to do that. One is I remember for my quantum mechanics courses that you can use imaginary potentials, imaginary K, you measure omega. But also there is a very well known that is this parasitic channel model. And in this case, it will be, I guess, possible to use another qubit to control.
So there is many technologies that are out there. There is something that is called fluxonium qubit. The fluxonium qubit is basically, you can imagine as a potential well that has 3 minima. And you define the qubit states as the ground state of each of those minima. And the reason you do that is because now it's the ground state only. It's very unsensitive to any noise from the environment. So you have a very isolated qubit. What is the problem? Well, I have a super isolated quantum system. How do I interact with it? So the people have tried many things with different approaches, try to optimize sensitivity to environment, try to optimize control, but everything comes at a trade-off. So there is no optimum technology out there that right now one could say, this is going to be the winner. We do not know. Yeah?
I assume to be
Yes. So like this example, this type of lattices that I have here, each qubit would actually be an electronic circuit with a Josephson junction. So then you can really have a very precise control over the distances and make it almost a perfect square lattice. But again, there is other technologies that are very hard to do that, like NV centers in diamond, which are a defect in the diamond lattice. You can create this effect by bombarding electrons into the diamond. But you immediately see that this is going to be stochastic, right? Where the defect is going to happen. So you will never be able to create. So it goes again back also to the question that you were having earlier, that each technology has an advantage and a trade-off. Yep.
Any other questions from the audience? I have one. I guess that it can be extended to more qubits, right? How is the scalability with the number of qubits regarding this specific protocol for one qubit?
So it actually scales with the number of back terms that you want to cancel. So it's the number of operators that describe leakage and phase error. So it's not as bad as scaling with the number of qubits and exponentially.
Any other question?
You mentioned that this can be done with Josephson junctions.
So I mean, like, one choice of qubit is the transmon that
Okay.
uses Josephson junction as a nonlinearity to create the anharmonic potential that I showed you at the beginning.
Well, that's limited by the temperature that you have to.
Yeah. So
as a visible technology that doesn't seem promising.
Exactly. So this is usually in the Diel fridge, right? And as you say, although you can read in the Diel fridge 4 millikelvin, the temperature where the device is running is not 4 millikelvin. So this is also something that, yeah, companies have to face, the scalability and how I can make a quantum computer that is really cold if I use Josephson junction such that I can do things there. Yeah, absolutely.
Any other question?
Thank you for the talk. I have one question about the noisy environment. What happens when the control, well, the external is just as noisy as system? They are comparable.
Yeah, I mean, so if your control is very noisy, right, then your rotation is going to be very bad. So the way around that is, instead of using coherent control where, say, the area of the pulse defines by how much you rotate, you change to adiabatic type controls that do not care about the noise that the pulse has, right? Okay. And then you can use something which is called shortcuts to adiabaticity to make also those protocols very fast, to avoid non-adiabatic transitions and generate those gates again in a timely fashion.
Yeah. Okay. I have.
Yeah.
I read sometime that linear computers can do quantum error correction.
So yes, but
But that's why.
so quantum error, you have to be careful, because when you say quantum computers can do quantum error correction, what it means is that just like in a classical machine, right? Right now, I don't know what is happening to the bits in my computer, but maybe one of them just flipped, right? And there is protocols there that make sure that if this happens, you still know if it was a 0 or a 1. So quantum error correction supposes that you can do those gates. You cannot quantum error correct the gate. You can quantum error correct the state. So if your gates are bad, your quantum error correction protocol is going to be very bad. So what we were saying a couple of years back is, sure, I can do quantum error correction, but if I'm introducing more errors the gates, then I will spend my time only doing quantum error correction instead of doing the algorithm.
Yeah.
Okay.
Thank you.
Yeah.
I just have a query that for this transmon,
Mhm.
is there any diagonal entanglement effect?
Oh, you mean here? I mean, yeah, of course. This will depend on the architecture that you have, right? Here I just chose these two examples to illustrate the type of problems that are happening right now with those architectures. But yeah, in reality, all of the qubits would become entangled with a tiny bit of spurious entanglement. It will really depend on how much you can turn off the long-range coupling in such architecture.
Thank you.
Yeah.
Any other question?
Quantum states.
We can do quantum control with quantum states.
Without quantum states. There's a new paper of Chris that states we can do quantum control without.
Yeah, I'm not sure I know what you're talking about.
Yeah, no.
So you have to show me the paper, and then
Okay.
I can maybe comment on that. Okay.
Any other question? One more question.
Yeah.
Do you know something about this Ribeiro atoms platform that's becoming more
Rydberg
popular
atoms.
now? Yeah. How is the quantum control there? Like,
So
does it work?
so it's the same thing. So if you don't know what a Rydberg atom is, right? A Rydberg atom is a very big atom that can be really modeled as a true two-level system, because the next orbital state is so high in energy that you will never actually be able to excite it. Now the issue comes again that when you put those Rydberg atoms in such a lattice and you shine radiation to excite one, the neighboring atom, its ground-based frequency is the same. So again, like your pulse, your optical pulse has a finite extent, so it will change the state of neighboring atoms. So one of the approach to mitigate that is actually to use two species of atoms that have different Rydberg transitions. But again, those two Rydberg transitions, they are different, but not infinitely. So crosstalk will happen.
You wouldn't be able to control the relative positions.
So
of the
these
Ribeiro atom.
with optical traps and optical tweezers, they can really make very precise lattices.
Hi, thanks for your talk. On your example, you were considering classical electromagnetic field.
Yeah.
How would it be different if you consider the quantum electromagnetic field? And in the practice, do you consider it classically or quantum electromagnetic field? How good approximation is to consider it classically instead of quantum?
Yeah. So this is real like radiation that you shine, right, on your qubit. It can be an electrical current or it can be a laser. But there you're in the limit of a very large photon number or a very large number of electrons. So the classical approximation holds. Now, you could do it quantum mechanically as well, but then like the interaction that I show where I have this fx cosine omega pt that couples to sigma x, this would not be the case. You would have to write something like sigma x times a dagger plus a, where it's the displacement of the electric field, for example. So this just makes the problem harder because you don't have a two-level system. You just have, many states, but the technique would work the same way.
We can consider that is a good approximation to handle it classically.
Yes, this perfectly works. You describe experiment very beautifully.
Thank you.
Yep.
Well, if there are no more questions, we thank again Hugo for such an interesting talk.
Thank you.
And thank you.